Chapter 1: Messengers of Humanity in the Infinite Cosmos. For millennia, humanity has consistently directed its gaze toward the celestial sphere, feeling an irresistible fascination for distant horizons and unreachable summits. The profound enigmas of the cosmos have constantly propelled the human spirit to explore the world around it, in an unceasing attempt to unravel the fundamental secrets of existence. This innate curiosity, this insatiable thirst for knowledge, has allowed us not only to meticulously map every corner of our terrestrial home, but also to make the most daring leap in our history, to venture into the cold, vast, and utterly inhospitable void that stretches beyond our atmosphere. Today, I invite you to embark on an extraordinary journey, a compelling and fascinating passage that will lead us beyond the limits of all that is known, traversing the very frontiers of the observable universe. Prepare yourself for a mental odyssey that will fundamentally challenge your perception of distance, time, and our true place in the cosmos. Our voyage will commence in the most remote, solitary regions of the solar system, alongside the brave space probes that abandoned our world decades ago, thus becoming the first steadfast ambassadors of humanity in interstellar space. Settle in comfortably, adjust the sound to your preference, and allow the night to gradually unveil the profound secrets of the universe. Welcome to Deep Space Calm, where every story represents a monumental step into the unknown. If you enjoy this type of cosmic voyage, please subscribe and leave a like to continue advancing together toward the most extraordinary depths of the cosmos. From these frontier regions, we will direct our course toward the nearest stellar system to our home, Alpha Centauri, a triple star system that has captured the imagination of scientists and dreamers alike. Our trajectory will then guide us toward magnificent stars such as Fomalhaut, Arcturus, and other nearby luminous beacons that shine brightly in our galactic neighborhood. Later in our journey, we will arrive at the dying giant CW Leonis, a magnificent star that will offer us a unique and invaluable window to comprehend the eternal cycle of stellar birth and demise that relentlessly shapes the universe. And subsequently, leaving these individual stellar marvels behind, we will undertake a truly thrilling expedition through the incomprehensibly vast expanses of the Milky Way galaxy. We will gaze with our own eyes, or rather, with the sophisticated instruments that extend our human vision, upon black holes of unimaginable masses, dark, cold clouds of interstellar dust where new stars are actively being born, and the brilliant, blazing remnants of gigantic suns that exploded millions of years ago. Finally, after definitively abandoning the far confines of our galaxy, we will travel so far away from our natal planet that we will reach the very boundaries of the visible part of the universe. And we will not be content with merely touching that distant horizon. We will conceptually traverse it to try and fully grasp how truly immense and perpetually mysterious the cosmos we inhabit truly is. This journey will be long, profoundly challenging for our imagination, and ultimately transformative for our understanding of the universe. Prepare yourself. We are about to begin. New Horizons, the probe that unveiled the face of Pluto. Mission, New Horizons. Launch date, January 19, 2006. Current distance from Earth, 52 astronomical units, approximately 7.8 billion kilometers. Escape velocity, 14 kilometers per second, equivalent to 3 astronomical units per year. Primary target, Pluto and its largest moon, Charon. Status of primary mission, completed with resounding success. Current status, operational, on extended mission. Like the majority of interplanetary research stations that venture toward the far reaches of the solar system, New Horizons performed a crucial gravitational assist maneuver near Jupiter before setting off toward its final, distant destination. This critical maneuver, executed with meticulous sub-millimeter precision in February of 2007, not only significantly boosted the spacecraft's speed, thereby reducing the total travel time by several years, but also provided scientists with an invaluable opportunity to capture high-resolution images of the solar system's largest gas giant and its fascinating, diverse family of satellites. Among the numerous scientific achievements obtained during this Jovian flyby, the most notable highlight is the capture of the very first high-definition video recordings of a volcanic eruption on Io, the closest of Jupiter's Galilean moons. These remarkable images demonstrated, with unprecedented detail, how towering volcanic plumes erupted and soared hundreds of kilometers above the surface of this hellish, tormented world, revealing the extraordinary geological activity relentlessly driven by the intense tidal forces that Jupiter exerts on its captive satellite. Only after successfully completing this scientifically productive encounter with Jupiter, and having gained the necessary additional momentum, did the probe undertake its long, 9-year journey toward its primary objective, the distant, enigmatic dwarf planet Pluto, which had been formally relegated to the category of dwarf planet just 1 year after the successful launch of New Horizons. The space station finally reached the vicinity of the Plutonian system in July of 2015, a historic moment that marked the very first close exploration of this frozen, distant world, which had remained a profound mystery for decades. The central and most ambitious objective of this mission was to conduct a multifaceted and exhaustive study of Pluto and its largest moon, Charon, which practically forms a binary system with Pluto due to their relatively comparable masses. The extensive scientific program included the essential capture of high-resolution photographs, the detailed creation of topographical maps of the surfaces of these icy celestial bodies, and the precise characterization of their chemical compositions. In addition to its advanced optical cameras, the sophisticated instruments carried by the probe accurately measured the faint magnetic fields in the close proximity of these worlds, meticulously analyzed the activity of the solar wind in this remote region of the solar system, and collected crucial data regarding the tenuous, wispy atmosphere of Pluto, primarily composed of nitrogen, methane, and carbon monoxide, as well as the reflectivity properties of their surfaces, ultimately revealing a world far more complex and geologically active than anyone had ever previously imagined. Of course, the ambitious research agenda also included the search for any still undiscovered satellites orbiting Pluto, though none were found beyond the 5 already known, and the essential refinement of the orbital parameters for the entire Plutonian system, fundamental data necessary for comprehending the long-term dynamics of this frontier region of our solar system. Once its primary mission, which spectacularly exceeded all scientific expectations, was successfully completed, the probe was far from retiring. New Horizons continued its onward journey beyond the orbit of Pluto, venturing even deeper into the mysterious Kuiper Belt, with the renewed goal of studying other frozen objects residing in that vast, dark region. On January 1, 2019, the probe performed a historic flyby of Arrokoth, initially designated as 2014 MU-69 and affectionately nicknamed Ultima Thule, a Kuiper Belt object that was revealed to have a peculiar contact binary shape resembling a snowman, thereby uncovering important secrets about the primordial formation process of the entire solar system. Furthermore, the probe's powerful cameras were utilized to carry out unique astrometric measurements, precisely determining the distances to nearby stars such as Proxima Centauri and Wolf 359 using the stellar parallax method. These measurements, taken from a position so incredibly far removed from the inner solar system, provided parallax values that are simply impossible to obtain from Earth, demonstrating how highly specialized space missions can unexpectedly make invaluable contributions to fundamental astronomy. Unfortunately, even the most successful space missions eventually have an expiration date. Starting in the year 2026, the plutonium-238 radioisotope thermoelectric generator (RTG) power source, which provides essential electrical energy to the probe, will begin to significantly degrade. This gradual power loss will inevitably force engineers to progressively deactivate the scientific instruments on board, one by one, to conserve the remaining energy. The top priority will be to maintain the communication systems operational for as long as humanly possible. The New Horizons station continues its relentless hyperspeed movement toward interstellar space, continuously speeding away from the Sun, and by the year 2038, if all technological systems remain operational as planned, the distance from the spacecraft to our star is projected to reach 100 astronomical units, approximately double the current distance of Pluto from the Sun. It is highly probable that by that time, the onboard power source of the station will have finally lost its capacity to generate sufficient electricity, rendering communication with it from Earth impossible. But New Horizons will not stop. The probe will travel along a hyperbolic orbit beyond the definitive gravitational boundaries of our solar system, slowly transforming into an interstellar artifact, a silent, powerful message from humanity destined to wander the galaxy for millions upon millions of years. It will never return to its home. A similar destiny, romantic and melancholic in equal measure, has already been experienced long ago by two other pioneering interplanetary probes that successfully abandoned our solar system decades earlier: Pioneer 10 and Pioneer 11. Pioneer 10, the first messenger in the cosmic ocean. Misión Pioneer 10. Launch date March 3, 1972. Estimated current distance from Earth 127 astronomical units, approximately 19 billion kilometers. Escape velocity approximately 12 kilometers per second, equivalent to 2.5 astronomical units per year. Primary target Jupiter and the space beyond. Status of primary mission completed with historic success. Current status out of operation, no communication since 2003. Pioneer 10 was the very first automated research station that humanity deliberately launched toward interstellar space, decisively marking the beginning of an entirely new era in space exploration. This brave and iconic probe successfully reached the Jupiter system on December 4, 1973, after having spent 641 days traveling through the inner solar system, becoming the first spacecraft to safely traverse the dangerous asteroid belt, a feat that many in the scientific community considered highly risky at the time. During its historic encounter with the massive gas giant, Pioneer 10 captured the first close-up images of Jupiter's turbulent atmosphere, recording detailed views of its distinct cloud bands and the iconic Great Red Spot with a clarity never before achieved. The probe also photographed several of the largest Galilean satellites, Io, Europa, Ganymede, and Callisto, providing the first precious close glimpses of these fascinating, diverse worlds. The scientific instruments aboard Pioneer 10 precisely measured the chemical composition of the Jovian atmosphere, which is overwhelmingly dominated by hydrogen and helium, and meticulously mapped the planet's intense magnetic field, revealing that it is far more powerful than initial predictions suggested. This magnetic field, approximately 20,000 times stronger than Earth's, traps charged particles, creating lethal radiation belts for any known life form. One of the most surprising discoveries made by Pioneer 10 was the definitive confirmation that Jupiter emits approximately 2.5 times more thermal energy into space than it receives from the Sun.
This groundbreaking finding revolutionized our existing understanding of gas giants, strongly suggesting that these massive planets still retain immense heat from their primordial formation 4.6 billion years ago, and that they are likely undergoing a slow gravitational contraction process that generates additional internal heat. The unique data collected by Pioneer 10 at the time became the fundamental basis for comprehending the internal structure of giant planets and the intrinsic nature of their diverse satellites. The trajectory of the twin probe, known as Pioneer 11, followed an equally fascinating path. Its route also passed close to Jupiter in December of 1974, utilizing the giant's enormous gravity to significantly modify its orbit, but its primary target was another colossal gas giant in our system, the magnificent Saturn, with its spectacular, intricate ring system. Pioneer 11 successfully reached Saturn in September of 1979, becoming the very first probe to visit this ringed planet. With the aid of its specialized measuring instruments, the spacecraft provided fundamental data on the planet's complex magnetic field and its intricate structures of radiation belts. The probe's cameras gifted us a large number of impressive images, not only of the gas giant itself and its complex ring system composed of countless ice particles, but also of some of its most intriguing satellites, such as Titan, the only moon in the solar system with a dense atmosphere, and Mimas, which features an impact crater so gigantic that it almost completely destroyed the satellite. According to current calculations based on its known trajectory and velocity, the distance between Pioneer 11 and the center of our solar system is now approximately 106 astronomical units, though its exact position is currently uncertain given that we have not had successful communication with the probe for decades. After brilliantly completing their main scientific programs, both Pioneer probes continued their relentless, inexorable journey, continuously moving farther away from the Sun and plunging into the deep interstellar void. Unfortunately, due to the progressive degradation of their radioisotope power sources and the weakening of their transmitters, the last signal successfully detected from Pioneer 10 was received in January of 2003, when the probe was situated at approximately 82 astronomical units from Earth. The signal was extraordinarily weak, barely distinguishable from the cosmic background noise. Pioneer 11, for its part, ceased communicating even earlier, in November of 1995, when it was at a distance of approximately 44 astronomical units. Both spacecraft are now continuing their silent passage through interstellar space, carrying within their structures the famous Pioneer plaque, designed by the great Carl Sagan and Frank Drake, which contains vital information about humanity and our precise location in the galaxy, intended for any possible extraterrestrial intelligence that might encounter them in the unimaginably distant future. It is now widely believed that the Pioneer probes are traveling rapidly beyond the definitive gravitational boundaries of the solar system, but they will never manage to catch two other spacecraft that have surpassed them, despite these latter craft being launched several years later. These are the legendary Voyagers, the most successful and longest-lived space explorers ever constructed by human hands. Voyager 1, the most distant human object in the cosmos. Mission, Voyager 1. Launch date, September 5, 1977. Current distance from Earth, 154 astronomical units, approximately 23 billion kilometers. Escape velocity, approximately 17 kilometers per second, equivalent to 3.6 astronomical units per year. Primary targets: Jupiter, Saturn, and interstellar space. Status of primary mission: completed with exceptional success.
Current status: limited operation, on interstellar mission. The monumental contribution of Voyager 1 to the exploration of the solar system and to the overall human knowledge of the cosmos simply cannot be overstated or undervalued. This extraordinary, iconic probe has borne witness to sights that no human being has ever directly contemplated, and it has expanded our understanding of the universe in ways that the most imaginative scientists of the 1970s could barely envision. During its close encounter with Jupiter in March of 1979, Voyager 1 discovered several previously unknown satellites orbiting the gas giant, as well as a delicate, previously unseen ring system. Voyager's high-resolution cameras captured spectacular images of fiercely active volcanic eruptions on Io, convincingly demonstrating that this satellite is the most geologically dynamic body in the entire solar system, with volcanoes forcefully expelling material hundreds of kilometers high above its yellow and red surface, which is colored by sulfur compounds. Voyager's images also showed, in a convincing and irrefutable manner, that Jupiter's Great Red Spot, observed from Earth for centuries, is indeed a gigantic, enduring anticyclonic storm, a monstrous hurricane larger than our entire planet, which has been raging violently in the Jovian atmosphere for at least 350 years, and possibly much longer. The spacecraft transmitted hundreds upon hundreds of mesmerizing images of the solar system's largest planet and its diverse entourage of satellites back to Earth, with each individual image revealing new mysteries and wonders. Following its tremendously successful encounter with Jupiter, Voyager 1 continued its journey towards Saturn, arriving in its proximity in November of 1980. The probe studied the planet's complex ring system in unprecedented detail, revealing thousands of individual ringlets and peculiar, intriguing structures, such as the dark spokes that seemed to momentarily defy known orbital mechanics. Voyager 1 also performed a close flyby of Titan, Saturn's largest moon, although its dense orange atmosphere prevented the cameras from successfully viewing the surface below. And after the station had fully completed its primary planetary exploration program and had subsequently crossed the orbit of Neptune, venturing into the most remote and previously unexplored regions of the solar system, its instruments began transmitting truly revolutionary data back to Earth concerning interstellar plasma, the galactic magnetic field, and the cosmic rays that constantly bathe our stellar neighborhood. This data provided the very first direct in situ measurements of the interstellar medium, the vast cosmic ocean in which the stars of our galaxy navigate. Voyager 1 has long since left behind the Kuiper Belt, the region of icy bodies beyond Neptune, and has successfully traversed the heliopause, the theoretical boundary where the solar wind definitively gives way to the rarefied interstellar gas that fills the expansive space between the stars. This historic crossing occurred in August of 2012, officially converting Voyager 1 into the first object ever manufactured by humanity to reach official interstellar space. The probe is now rapidly traversing the scattered disk region of the solar system, heading toward the inner boundary of the hypothetical Oort cloud, a gigantic spherical shell of comets that completely envelops the solar system at a distance that may extend up to 100,000 astronomical units from the Sun. At this very moment, Voyager 1 is not only the object manufactured by human beings that is farthest from Earth, but it also holds the undisputed record for being the fastest spacecraft in terms of solar system escape velocity among all human creations. Its velocity relative to the Sun is approximately 17 kilometers per second, which equates to more than 61,000 kilometers per hour. As the first space probe to venture so profoundly beyond the limits of the Sun's domain,
Voyager 1 offered scientists a truly unique and unrepeatable opportunity to study the heliopause and its characteristics in situ. This is the name given to the region of space surrounding our star where the immense pressure of the solar wind, that constant, relentless flow of charged particles emanating from the Sun at supersonic speeds, finally balances with the pressure exerted by the rarefied interstellar gas that fills the space between the stars. The continuous collision of charged particles emitted by our star with the surrounding interstellar plasma generates intricate and highly complex structures of elemental particles and intertwined magnetic fields, the detailed study of which is extremely important for comprehending the fundamental physical processes that occur throughout the universe, ranging from the formation of new stellar systems to the propagation of high-energy cosmic rays across the entire galaxy. Chapter 2. Our closest stellar neighbors. Unfortunately, despite the impressive performance and exceptional longevity of Voyager 1, its twin, Voyager 2, will inevitably also begin to experience significant issues with its vital power supply in the coming years. The radioisotope thermoelectric generators, RTGs, installed on both spacecraft rely on the heat generated by the natural disintegration of plutonium-238, a process that inexorably decreases over time, following the immutable laws of nuclear physics. The half-life of this particular isotope is approximately 87.7 years, which means that with every 9 decades that pass, the quantity of radioactive material is precisely halved, and with it, the thermal energy available to generate necessary electricity. By the year 2025, the available power output on the Voyager probes will have diminished to such a critical point that NASA engineers will be forced to make extremely difficult decisions regarding which instruments to keep operational and which to permanently deactivate. Every single watt of power will become precious, and it will be necessary to carefully prioritize between maintaining the essential communication systems active or continuing to diligently collect scientific data about the interstellar medium. Scientists currently hope to be able to maintain at least a few key instruments functioning until approximately 2030, at which time the available energy is projected to fall below the critical threshold required to operate even the most basic systems. When that inevitable moment arrives, the Voyagers will continue their silent, profound journey through interstellar space, transformed into mute, enduring artifacts of a technological civilization. Each carries with it a meticulously crafted golden record engraved with sounds and images of Earth, the famous Voyager Golden Record, designed by a dedicated team led by the brilliant astronomer Carl Sagan. This remarkable disk contains greetings in 55 languages, music from different cultures and epochs, natural sounds of our planet, and 116 images that visually depict the rich diversity of life and terrestrial cultures. It is a cosmic message in a bottle, launched into the vast ocean of space with the remote hope that one day, perhaps millions or even billions of years from now, it might be found by some intelligent extraterrestrial entity. According to current trajectory projections, in approximately 40,000 Earth years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445, located in the constellation of Camelopardalis, the giraffe. Voyager 2, for its part, will approach the star Ross 248 in the constellation of Andromeda, also in about 40,000 years. However, both probes will simply continue their slow, silent drift through intergalactic space, never stopping their forward momentum, converted into eternal cosmic nomads. The legacy of these 4 pioneering missions, New Horizons, Pioneer 10 and 11, and the 2 Voyagers, is truly incalculable and transformative. They fundamentally reshaped our understanding of the outer solar system, revealing worlds of complexity and alien beauty that defied all previous expectations. They demonstrated that deep space exploration is not only possible but necessary, proving that we can successfully send robotic emissaries to places where no human being will be able to travel for centuries, perhaps millennia. And now, as these magnificent vessels speed away from us at velocities that challenge human intuition, carrying profound messages from our civilization, it is our turn to continue the journey mentally, following their projected trajectories out toward the nearest stars. Having bid farewell to these courageous mechanical explorers, our imaginative journey now takes us toward the first truly interstellar destination, the closest stellar system to our Sun. Alpha Centauri is the collective name given to this group of stars that has fascinated professional astronomers, science fiction writers, and dreamers for countless generations. It represents the crucial first real step toward the stars, the absolute closest neighbor in the vast, dark, interstellar desert that surrounds our solar home. The Alpha Centauri system is, in fact, a triple star system, composed of 3 stars that dance gravitationally in a complex, enduring cosmic choreography. The immense distance separating us from this system is approximately 4.37 light-years, which is equivalent to about 41.3 trillion kilometers, or roughly 276,000 astronomical units. This staggering figure, although it represents the shortest distance to any neighboring stellar system, is so overwhelmingly vast that it fundamentally challenges our intuitive human comprehension. To put this monumental distance into proper perspective, if we were able to travel at the speed of Voyager 1, the fastest spacecraft we have ever successfully launched into interstellar space, it would still take us approximately 73,000 years to reach Alpha Centauri. The 2 primary stars of the system, designated Alpha Centauri A and Alpha Centauri B, form a close binary pair that orbits around a common center of mass. Alpha Centauri A is slightly larger and more luminous than our Sun, possessing a mass approximately 1.1 times the solar mass and a luminosity around 1.5 times greater. Its surface temperature is similar to that of the Sun, hovering around 5,800 Kelvin, which gives it a characteristic yellowish color, very much like our own star. Alpha Centauri B, conversely, is somewhat smaller and dimmer, with approximately 0.9 solar masses and a luminosity of only 45% of the Sun's. Its surface temperature is slightly cooler, around 5,300 Kelvin, lending it a pale orange hue. These 2 stars orbit one another with a period of approximately 79.91 Earth years, approaching a minimum distance of 11.2 astronomical units, roughly the distance between the Sun and Saturn, and moving apart to 35.6 astronomical units at the most distant point of their elliptical orbit. The third component of the system, Proxima Centauri, is technically the closest star to us, situated at a mere 4.24 light-years away. However, this is a tiny, incredibly dim red dwarf, possessing barely 12% of the Sun's mass. Proxima orbits the binary pair Alpha Centauri AB at an enormous distance of approximately 13,000 astronomical units, so far away that some astronomers debate whether it is genuinely gravitationally bound to the system or if it is merely passing nearby in cosmic terms. Its orbit around the main pair, assuming it is indeed bound, would take approximately 550,000 years to complete. What makes Proxima Centauri particularly fascinating to astrobiologists and seekers of extraterrestrial life is that it harbors at least 2 confirmed planets orbiting it. The most notable is Proxima Centauri B, discovered in August of 2016, a rocky world with an estimated mass of at least 1.17 times the mass of Earth. This exoplanet orbits its parent star at a mere distance of 0.05 astronomical units, completing one orbit every 11.2 Earth days. Although this distance might seem to place it dangerously close to its star, given that Proxima is a much cooler and fainter red dwarf than the Sun, the planet is situated precisely within the so-called habitable zone, where liquid water could potentially exist on its surface. However, any life on Proxima Centauri b, if it exists, would face formidable challenges. Red dwarfs, such as Proxima, are notoriously known for their violent stellar activity, producing frequent, intense stellar flares that bathe their nearby planets with potentially sterilizing ultraviolet and X-ray radiation. Furthermore, a planet orbiting so closely to its star would likely be in synchronous rotation, with one hemisphere permanently illuminated and the other plunged into eternal, frozen darkness, creating extreme climatic conditions. Beyond Alpha Centauri, at a distance of approximately 5.96 light-years, we find Barnard's star, the second closest individual star to us after Proxima Centauri, if we don't consider the triple system as a single unit. Named in honor of the American astronomer Edward Emerson Barnard, who precisely measured its high proper motion in 1916, this red dwarf is notable for having the highest apparent proper motion observed from Earth, visibly shifting across the sky at an angular velocity of approximately 10.3 arcseconds per year. Barnard's star is a cosmic elder, with an estimated age of between 7 billion and 12 billion years, significantly older than our 4.6 billion-year-old Sun. This great antiquity is reflected in its extremely low metallicity, barely 10 to 32% of the solar metallicity, indicating that it formed during an epoch when the universe had far fewer heavy elements available. With only 14% of the Sun's mass and a luminosity of a mere 0.4% of the Sun's output, this red dwarf is a prime example of the most common type of star found in our galaxy, although they are so dim that no red dwarf is visible to the naked eye from Earth, despite their great abundance. For decades, astronomers speculated about the possibility of planets orbiting Barnard's star. In 1963, astronomer Peter Van de Kamp claimed to have detected wobbles in the star's motion that suggested the presence of one or even two giant planets. However, these claims were later proven to be erroneous, the result of systematic errors in the measurements. It wasn't until 2018 that the tentative discovery of a real planet was announced, Barnard's star B, a super-Earth with a minimum mass of approximately 3.2 times the mass of Earth, orbiting at a distance of 0.4 astronomical units, with a period of 233 days. However, this discovery still requires definitive confirmation through additional corroborating observations. Continuing our deep journey through the solar neighborhood, we next arrive at Wolf 359, a red dwarf located approximately 7.86 light-years away in the constellation Leo. This tiny star possesses only 9% of the Sun's mass and a luminosity of barely 0.1% of the solar output, rendering it invisible to the naked eye, despite its relative closeness. Wolf 359 is also a flare star, a BY Draconis variable that experiences pronounced fluctuations in its brightness due to massive star spots and dramatic flares on its surface. Interestingly, Wolf 359 has gained a certain notoriety in popular culture, having been mentioned in several episodes of the Star Trek franchise, including the famous disastrous encounter with the Borg in The Battle of Wolf 359. This fictional battle has consequently made the name of this dark, obscure star more widely known among the general public than many far brighter and more prominent stars in the night sky. At a distance of approximately 8.29 light-years, we find Lalande 21185, yet another red dwarf in the constellation Ursa Major, the Great Bear. With approximately 46% of the Sun's mass and only 2.2% of its luminosity,
This star exhibits a notable proper motion of 4.8 arcseconds per year, the third highest proper motion known after Barnard's star and Kapteyn's star. For decades it was suspected that this star might harbor planets, but systematic searches have not definitively confirmed any worlds orbiting it to date. Our next stellar destination is the binary system formed by Sirius A and Sirius B, located at approximately 8.6 light-years away in the constellation Canis Major, the Greater Dog. Sirius A is the brightest star in the terrestrial night sky, with an apparent magnitude of -1.46, and it has played a significant guiding role in the mythology and celestial navigation of countless human cultures throughout history. The ancient Egyptians, for example, based their calendar on the heliacal rising of Sirius, which coincided precisely with the annual flooding of the Nile River, a crucial, life-giving event for their agricultural civilization. Sirius A is a main sequence star of spectral type A1V, significantly larger and hotter than our Sun, possessing approximately double its mass and a luminosity 25 times greater. Its surface temperature reaches about 9,940 Kelvin, giving it its characteristic brilliant blue-white color. With an estimated age of only 242 to 250 million years, Sirius A is relatively youthful compared to our 4.6 billion-year-old Sun. Its companion, Sirius B, is a white dwarf, the dense, compact remnant core of a star that has already successfully completed its main sequence life and ejected its outer layers. With a mass approximately equal to that of the Sun, compressed into a volume roughly the size of the Earth, Sirius B possesses an astonishing, mind-bending density of approximately 1 million times that of water. A single teaspoon of its material would weigh more than 5 tons on the Earth's surface. This incredible white dwarf orbits Sirius A with a period of approximately 50 years, at a distance that varies between 8.2 and 31.5 astronomical units. Chapter 3: Giants and Dwarfs of the Cosmic Neighborhood. At a distance of approximately 11.46 light-years from our solar system, we encounter another fascinating stellar binary system, Procyon. This system is composed of Procyon A, a yellowish-white subgiant star that proudly stands as the 8th brightest star in the terrestrial night sky, and its faint, diminutive companion, Procyon B, another white dwarf star similar to Sirius B. The name Procyon derives from the Greek, meaning "before the dog," a reference to the fact that this star rises above the horizon just before Sirius, the dog star, when observed from middle latitudes in the northern hemisphere. Procyon A possesses approximately 1.5 times the mass of the Sun and shines with a luminosity nearly 7 times greater than our star. With an estimated age of around 1.87 billion years, this star has already evolved beyond the main sequence stage and is now classified as a subgiant. This classification means it has exhausted the supply of hydrogen fuel in its core and is currently consuming hydrogen in a shell surrounding an inert helium core. In the cosmic future, several hundreds of millions of years from now, Procyon A is destined to expand dramatically into a bloated red giant before it ultimately expels its outer layers, leaving behind another dense, Earth-sized core known as a white dwarf. Its companion, Procyon B, has already completed this full evolutionary cycle. This white dwarf has a mass of approximately 0.6 solar masses and orbits Procyon A with a period of 40.8 years, at a distance that varies between 8.9 and 21 astronomical units. Despite its considerable mass, Procyon B is exceptionally dim, shining with only 0.00049 times the luminosity of the Sun,
making it extraordinarily challenging to observe directly due to the overwhelming, blinding glare emanating from its brighter, larger companion. Continuing our journey ever farther away from the solar system, we arrive at Tau Ceti, a solitary star located approximately 11.9 light-years away in the constellation Cetus, the Whale. This star has captured the imagination of both rigorous scientists and speculative science fiction writers due to its notable similarity to our Sun. With a mass of approximately 0.78 solar masses and a luminosity of 52% of the solar output, Tau Ceti is one of the most Sun-like stars in our immediate cosmic neighborhood, though it is slightly smaller and less brilliant. What makes Tau Ceti particularly interesting from an astrobiological standpoint is that it appears to harbor a complete planetary system. High-precision spectroscopic observations have revealed compelling evidence of at least 5 candidate planets orbiting this star, although definitive confirmation of all of them is still pending. 2 of these potential worlds, tentatively designated as Tau Ceti E and Tau Ceti F, could be situated within the star's habitable zone, where temperatures would theoretically allow for the persistent existence of liquid water on the surface. However, life on any planet orbiting Tau Ceti would face a significant and potentially devastating challenge. The star is encased by an extremely dense debris disk, which is estimated to be approximately 10 times more massive than the Kuiper Belt in our own solar system. This massive disk contains countless comets and asteroids that regularly bombard the inner planets with catastrophic impacts. The rate of collisions on the planets of Tau Ceti could be up to 10 times higher than what Earth experienced during the destructive period of the late heavy bombardment, 4 billion years ago, which would make the development and sustained evolution of complex life forms extremely difficult, though not necessarily impossible, depending on the protective layers afforded by the planetary atmospheres. Now our journey takes us considerably farther, leaping past the close stars of the immediate solar neighborhood toward more distant but equally fascinating targets. At a distance of approximately 25.1 light-years, we encounter Fomalhaut, also known as Alpha Piscis Austrini, the brightest star in the constellation Piscis Austrinus, the southern fish. This young, luminous star of spectral type A3V has approximately 1.9 times the mass of the Sun and shines with a luminosity 16.6 times greater, boasting a surface temperature of around 8,590 Kelvin, which lends it a beautiful, bright, bluish-white color. With an estimated age of only 440 million years, Fomalhaut is a relatively youthful star that is still fully stable on the main sequence, steadily fusing hydrogen in its core. What makes Fomalhaut truly exceptional is its spectacular circumstellar debris disk, which is one of the brightest and most thoroughly studied structures of its kind in the entire galaxy. This vast ring, which stretches from approximately 133 to 158 astronomical units from the star, was one of the very first such structures to be directly photographed, successfully captured by the Hubble Space Telescope in visible light. The structure of the Fomalhaut disk is notably asymmetrical, featuring an extremely sharp and well-defined inner edge that strongly suggests the pervasive presence of one or more planets that are dynamically and gravitationally sculpting the disk through sustained orbital interactions. In 2008, astronomers initially announced the discovery of Fomalhaut B, seemingly a giant planet directly photographed in visible light moving within the inner gap of the disk. However, subsequent higher-resolution observations have generated controversy over the true nature of this object, with some scientists now suggesting it might actually be a rapidly expanding cloud of debris resulting from a sudden, catastrophic collision between 2 large planetesimals, similar to the giant impact thought to have formed Earth's moon. Advancing still further in our interstellar voyage, we arrive at Arcturus, also known as Alpha Bootis, located approximately 36.7 light-years away in the constellation Boötes, the herdsman. Arcturus is the fourth brightest star in the terrestrial night sky and the brightest star in the entire northern celestial hemisphere. Its name is derived from the ancient Greek, meaning guardian of the bear, referencing its position near the constellations Ursa Major and Ursa Minor. Arcturus is an orange giant of spectral type K03, a star that has evolved well beyond the main sequence after exhausting the vital hydrogen fuel in its core. With approximately 1.08 solar masses, but a radius approximately 25.4 times the radius of the Sun, Arcturus has expanded enormously during its evolutionary phase. If this star were placed at the center of our solar system, its surface would extend significantly beyond the orbit of Mercury, completely engulfing that inner planet. Despite having a mass similar to the Sun's, Arcturus shines with a colossal luminosity, approximately 170 times greater, now powered by the fusion of helium into carbon and oxygen deep within its core. The surface temperature of Arcturus is about 4,290 Kelvin, which is significantly cooler than the Sun's, granting it its characteristic reddish-orange color. This star possesses an unusually low metallicity for a star of its type, with only around 22 to 35% of the abundance of heavy elements found in the Sun, suggesting it formed in a much earlier epoch of galactic history, when the interstellar medium contained fewer heavy elements produced by preceding generations of stars. Arcturus also exhibits an extremely high proper motion across the sky, visibly displacing at approximately 2.3 arcseconds per year. Kinematic studies have revealed that this star does not belong to the Milky Way's thin disk, like our Sun, but is likely a member of the so-called Arcturus stream, a group of ancient stars that share a common trajectory through the galaxy. It is widely believed that these stars may be the scattered remnants of a dwarf galaxy that was captured and gravitationally torn apart by the mighty Milky Way billions of years ago, with its individual stars now scattered into peculiar orbits around the galactic center. Our next destination takes us to Vega, also known as Alpha Lyrae, situated approximately 25 light-years away in the constellation Lyra, the Lyre. Vega is the fifth brightest star in the night sky and the second brightest in the northern celestial hemisphere after Arcturus. This star has played a fundamental role in the history of astronomy. It was the first star, other than the Sun, to be successfully photographed, the first celestial body whose spectrum was reliably recorded, and it served as the critical zero reference point on the stellar magnitude scale for many decades. Vega is a main sequence star of spectral type A0V, approximately 2.1 times more massive than the Sun and boasting a luminosity 40 times greater. Its surface temperature reaches an impressive 9,602 Kelvin, giving it a brilliant blue-white color. With an estimated age of only 455 million years, Vega is relatively young and is expected to remain on the main sequence for approximately another 500 million years, before beginning its evolution toward the giant stage. A notable and extraordinary characteristic of Vega is its extreme rotation speed. The star spins rapidly on its axis at approximately 236 kilometers per second at its equator, which corresponds to a rotation period of only 12.5 hours, unbelievably fast when compared to the Sun's leisurely 25 days. This dizzying rotation causes Vega to be significantly oblate, flattened, with its equatorial diameter approximately 23% larger than its polar diameter, effectively turning it into an oblate spheroid rather than a perfect sphere. Like Fomalhaut, Vega is surrounded by a vast, dusty circumstellar debris disk, which was first discovered in 1983 by the IRAS infrared satellite.
This disk extends from about 86 to 200 astronomical units from the star and emits an excess of infrared radiation, characteristic of warm dust heated by the stellar light. The structure of the disk suggests the compelling presence of yet undetected planets that are gravitationally clearing regions of the disk, although to date, no planet around Vega has been definitively confirmed through either direct or indirect detection methods. Continuing our tour of increasingly distant stars, we arrive at Altair, also known as Alpha Aquilae, located approximately 16.7 light-years away in the constellation Aquila, the Eagle. Altair is the 12th brightest star in the night sky and forms part of the prominent Summer Triangle asterism, along with Vega and Deneb, a shape easily recognizable during the summer months in the northern hemisphere. Altair is a main sequence star of spectral type A7V, with approximately 1.8 solar masses and a luminosity nearly 11 times that of the Sun. Its surface temperature is around 7,550 Kelvin, giving it a bright white color. Much like Vega, Altair rotates extraordinarily quickly on its axis, completing one full rotation in approximately 8.9 hours. This breakneck rotation also causes the star to be significantly flattened, with an equatorial radius approximately 22% larger than its polar radius. Altair's rapid rotation has another fascinating effect. It creates a substantial temperature gradient between the star's equator and its poles. Due to a phenomenon known as gravity darkening, the polar regions of Altair, which rotate slower and are less flattened, are approximately 2,000 Kelvin hotter than the equatorial regions. This means the poles shine more intensely and appear whiter, while the equator is dimmer and more reddish. This intricate effect has been confirmed through high-resolution interferometry, making Altair one of the few observed cases where we can directly study the non-uniform surface temperature of a distant star. Chapter 4: Dying Stars and Exotic Objects. Our journey now leads us toward one of the most fascinating and enigmatic objects in our extensive cosmic neighborhood, CW Leonis, also famously known by its catalog designation IRC +10216. This star is situated at an estimated distance of approximately 500 light-years from Earth in the constellation Leo, the Lion. Although this distance may seem immense when compared to the close-by stars we have visited thus far, CW Leonis demands special attention because it represents a perfect, illuminating example of the final stages of stellar evolution, offering us a unique, invaluable window into the eventual fate that awaits stars like our Sun in the distant cosmic future. CW Leonis is a carbon giant star in the advanced phase of the asymptotic giant branch, AGB, an evolutionary stage that low and intermediate mass stars undergo after they have fully exhausted both the hydrogen and the helium in their cores. During this critical phase, the star experiences periodic thermal pulses where alternating shells of helium and hydrogen ignite in explosive nuclear fusion reactions, causing the star to dramatically expand and contract. These massive pulses eject colossal quantities of stellar material into the surrounding space, creating a dense, complex, and opaque envelope of gas and dust that completely shrouds the central star. The envelope of CW Leonis is so immensely dense that the central star is rendered completely invisible at optical wavelengths, hidden behind opaque clouds of carbon dust and complex organic compounds. It is only in the infrared and at radio wavelengths that we can successfully penetrate this thick curtain of material and study the intense physical processes occurring within this stellar cocoon. The rate of mass loss from CW Leonis is truly astonishing.
Approximately 1 Earth mass every single year is steadily stripped away from the star and forcefully flung out into interstellar space at velocities of around 15 kilometers per second. This process of massive matter ejection not only marks the terminal phase of the star's life, but also plays an absolutely crucial role in the chemical enrichment of the interstellar medium. The nuclear reactions that have occurred deep within CW Leonis for millions of years have meticulously synthesized heavy elements that did not exist when the star initially formed. Carbon, nitrogen, oxygen, and dozens of other chemical species produced in the fierce nuclear furnace of the stellar interior are now liberated into space, where they will eventually be incorporated into the next generations of stars, planets, and possibly even complex life forms. Astronomers have successfully detected more than 80 different molecular species within the extended envelope of CW Leonis, making it the space object with the richest known molecular chemistry to date, surpassing even the giant molecular clouds where new stars are born. Among these molecules are complex organic compounds, such as cyanopolyeins, polycyclic aromatic hydrocarbons, and even prebiotic molecules that could potentially have played a significant role in the origin of life on planets like Earth billions of years ago. The observation of CW Leonis and similar stars allows us to gain a deeper, more accurate understanding of how stars are born and how they meet their demise, completing the pervasive cosmic cycle that inherently connects generations of stars throughout time. Within a few thousand years in cosmic terms, a mere blink of an eye, CW Leonis will have completely ejected its outer layers, leaving behind a dense, intensely hot core that will transition into a white dwarf. The ejected envelope, illuminated by the intense ultraviolet radiation from the exposed core, will brilliantly shine as a colorful planetary nebula for a few thousand years before eventually dispersing completely into the interstellar medium, thereby returning to the galaxy the heavy elements forged in the stellar interior. Leaving behind the dying CW Leonis, our imaginary journey now plunges us into the vast depths of the Milky Way, where we will encounter some of the most extreme and fascinating objects in the known universe. Among these stand out the stellar giants and supergiants, celestial bodies of truly epic proportions that fundamentally challenge our conventional understanding of what a star can truly be. Consider, for example, Betelgeuse, the famous red supergiant that marks the left shoulder of the constellation Orion, the Hunter. Situated at approximately 548 light-years away, this titanic star has a physical radius of approximately 764 times the radius of the Sun, according to the most recent estimations. If Betelgeuse were to replace our Sun at the center of the solar system, its surface would extend far beyond the orbit of Mars, completely engulfing Mercury, Venus, Earth, and the Red Planet. The sheer volume of this monstrous star is so immense that it could contain approximately 400 million suns within its boundaries. Despite its colossal size, Betelgeuse has a relatively moderate mass of only 16 to 19 times the solar mass, which means its average density is extraordinarily low, millions of times less dense than the very air we breathe at sea level on Earth. The outer atmosphere of Betelgeuse is so tenuous that it would technically be considered a near-perfect vacuum by terrestrial standards, and yet, due to the star's gigantic volume, it contains more total mass than our entire Sun. Betelgeuse is in an advanced stage of its stellar evolution, having already exhausted the hydrogen fuel in its core, and now fusing increasingly heavier elements in concentric shells within its interior. The star's core is currently fusing helium into carbon and oxygen, while upper layers are still burning hydrogen. This crucial multi-layered structure makes the star inherently unstable, causing it to experience irregular pulsations that lead to dramatic variations in its brightness and apparent size. At some point in the near future, in astronomical terms, it could be as soon as tomorrow or as far off as 100,000 years, no one knows for certain, Betelgeuse will finally exhaust its ultimate nuclear fuel and catastrophically collapse in a fraction of a second, rebounding in a spectacular supernova explosion that will shine so intensely that it will be easily visible in broad daylight from Earth, possibly appearing as bright as the full moon for several weeks. The collapsed core will most likely leave behind a neutron star or possibly even a stellar mass black hole, while the outer layers, richly enriched with heavy elements forged in the explosion, will disperse violently through interstellar space, successfully seeding future generations of stars and planets. Another notable giant is Antares, the red supergiant that marks the heart of the constellation Scorpius, the Scorpion. Situated at approximately 550 light-years away, Antares has a radius of approximately 680 times the solar radius, slightly smaller than Betelgeuse, but equally impressive in scale. The name Antares derives from the Greek and means rival of Ares, or anti-Mars, referring to its intense reddish color which rivals the hue of the red planet when both objects appear close together in the night sky. With an estimated mass of 12 times the solar mass and a staggering luminosity, approximately 57,500 times that of the Sun, Antares is a truly titanic star. Its surface temperature is relatively low, around 3,500 Kelvin, which gives it its characteristic deep red color. But the immense surface area compensates for this relatively cool temperature, causing the star to shine with an astonishing total luminosity. The majority of this prodigious energy output is emitted in the infrared spectrum, invisible to our human eyes but readily detectable with specialized instruments. Antares also has a stellar companion, Antares B, a hot main-sequence star of type B that orbits the supergiant at an average distance of approximately 529 astronomical units, with an orbital period of about 878 years. This smaller but much hotter companion appears blue-green, creating a beautiful and striking contrast with the intense red of Antares A when observed through a powerful telescope. The presence of this companion allows astronomers to more accurately calculate Antares' mass and gain a better understanding of its complex evolution. But even giants as immense as Betelgeuse and Antares are dwarfed by some of the largest stars currently known in our galaxy. UY Scuti, located approximately 9,500 light-years away in the constellation Scutum, the Shield, is arguably one of the largest stars ever discovered in terms of sheer volume. Its radius is estimated to be approximately 1,700 times the radius of the Sun, though these measurements are extremely challenging and are subject to large uncertainties. If UY Scuti were to replace the Sun, its surface would extend well past the orbit of Jupiter, a distance so vast that light would take more than 6 hours to travel from the core to the star's surface. Despite its incomprehensible size, UY Scuti has a surprisingly modest mass of only approximately 7 to 10 times the solar mass, which grants it an average density even lower than that of Betelgeuse. The star is currently losing mass at a prodigious rate, ejecting approximately 1 solar mass every 1,000 years in the form of powerful stellar winds. This massive material loss creates an extended envelope of gas and dust surrounding the star, making it exceptionally difficult for scientists to precisely determine where the stellar photosphere truly ends and where the circumstellar envelope truly begins. Chapter 5. Black Holes, Neutron Stars, and Cosmic Nebulae. At the opposite extreme of the stellar spectrum, we encounter white dwarfs,
objects that represent the final, inevitable destiny of stars similar in mass to our Sun. These stellar relics are incredibly dense and compact, condensing approximately the entire mass of the Sun into a volume roughly the size of the Earth. The most famous and thoroughly studied white dwarf star is likely Sirius B, the faint companion to the brilliant Sirius A, which we mentioned earlier in our cosmic journey. Sirius B has a mass of approximately 1.02 solar masses, compressed into a radius of just 5,800 kilometers, only slightly smaller than the Earth's radius. This results in an overwhelming average density of approximately 1 million times the density of water. A single cubic centimeter of Sirius B's material would weigh approximately 1 metric ton if we were able to successfully transport it to the terrestrial surface. This extreme density is made possible by a fundamental quantum phenomenon called electron degeneracy pressure, where electrons are compressed so closely together that the principles of quantum mechanics, specifically the Pauli exclusion principle, prevent any further compression from occurring. Despite having a mass comparable to the Sun's, Sirius B shines with only 2.4% of the solar luminosity. This relatively low luminosity is not due to active nuclear reactions, as white dwarfs have no nuclear fusion occurring in their interiors. Instead, they shine merely by the residual heat remaining from their formation, cooling slowly over many billions of years. The surface temperature of Sirius B is approximately 25,000 Kelvin, much hotter than the Sun's surface, but its minuscule surface area means it emits a far smaller total amount of energy. White dwarfs have a fundamental mass limit known as the Chandrasekhar limit, calculated by the brilliant Indian astrophysicist Subrahmanyan Chandrasekhar in 1930. This limit, which is approximately 1.4 solar masses, represents the maximum mass a white dwarf can possess while remaining stable. If a white dwarf accumulates material from a companion star and surpasses this critical limit, the electron degeneracy pressure can no longer support the star against catastrophic gravitational collapse. The devastating result is a runaway thermonuclear explosion known as a Type Ia supernova, where the white dwarf is completely obliterated in a stellar conflagration that briefly surpasses the light output of an entire galaxy. These Type Ia supernovae are immensely important for modern cosmology because they all possess approximately the same intrinsic brightness, which effectively makes them standard candles that astronomers can use to accurately measure vast cosmological distances. It was precisely through the observation of distant Type Ia supernovae that astronomers discovered in 1998 that the expansion of the universe is accelerating, a groundbreaking finding that led to the proposal of the mysterious dark energy, and which was awarded the Nobel Prize in Physics in 2011. But if the collapsing core of a massive star plunges past the point where even electron degeneracy pressure can halt it, the result is even more extreme, a neutron star. These objects represent some of the densest states of matter known in the universe, with densities that closely approximate those of the atomic nucleus itself. A typical neutron star has a mass of approximately 1.4 solar masses compressed into a sphere only 20 to 25 kilometers in diameter, which is smaller than most terrestrial cities. The density of a neutron star is so extreme that a single grain of rice-sized amount of its material would weigh as much as all of humanity combined. A cubic centimeter of neutron star material would have a mass of approximately 400 million metric tons. This incredible density is sustained by neutron degeneracy pressure, a quantum phenomenon similar to electron degeneracy pressure, but operating at even greater densities, where protons and electrons have been forced to combine, forming pure neutrons. Neutron stars are born in the violent supernova explosions of massive stars. When the core of a star with more than approximately 8 solar masses exhausts its nuclear fuel, it collapses in a mere fraction of a second, compressing matter to unimaginable densities.
Protons and electrons merge to form neutrons, releasing an avalanche of neutrinos that escape the collapsing core, carrying away 99% of the explosion's total energy. The resulting shockwave explodes outward through the star's outer layers, expelling them into space in a brilliant supernova, while the collapsed core remains behind as a newly formed neutron star. Many neutron stars spin at breakneck speeds, completing hundreds of rotations every single second. These objects, known as pulsars, emit concentrated beams of electromagnetic radiation from their magnetic poles that sweep across space like the powerful beams of a cosmic lighthouse. When these beams happen to point toward Earth during each rotation, we successfully detect regular pulses of radiation with a precision that rivals the best terrestrial atomic clocks. The fastest known pulsar, PSR J1748-2446 AD, rotates approximately 716 times per second, which means its equatorial surface is moving at approximately 24% of the speed of light. The magnetic fields of neutron stars are the most intense known in the universe, typically 1 billion times stronger than Earth's magnetic field. A special subclass of neutron stars called magnetars possess even more extreme magnetic fields, up to 1,000 times more intense than normal pulsars. These magnetic fields are so powerful that they literally distort the quantum structure of the empty space surrounding the star, causing the vacuum to behave like a refractive medium that polarizes the light passing through it. But even neutron stars have a maximum mass limit, known as the Tolman-Oppenheimer-Volkoff limit, above which not even neutron degeneracy pressure can support the star against gravitational collapse. This limit is not known with exact precision because it depends critically on the equation of state of dense nuclear matter, something which is still not fully understood, but it is estimated to be approximately 2 to 3 solar masses. If the collapsed core of a supernova exceeds this TOV limit, nothing in the universe can halt the collapse, and the result is the most extreme and mysterious object known to physics, a black hole. Black holes are regions of space-time where gravity is so overwhelmingly intense that nothing, not even light, can escape once it crosses the event horizon, the boundary of the point of no return. The theoretical existence of these objects was predicted by Einstein's theory of general relativity in 1915, although Einstein himself doubted they could truly exist in nature. It wasn't until decades later that astronomers began finding convincing observational evidence of their existence. Stellar mass black holes, formed by the collapse of massive stars, typically have masses of approximately 3 to 20 solar masses and event horizon diameters ranging from only a few kilometers up to about 120 kilometers. Despite their name, black holes are not truly hollow or empty. All the mass of the collapsed star is concentrated into an infinitesimally small singularity at the center, surrounded by the event horizon that marks the crucial point where the escape velocity equals the speed of light. Near the event horizon of a black hole, the effects of general relativity become extreme and counterintuitive. Time significantly slows down compared to time measured by distant observers, a phenomenon known as gravitational time dilation. To an external observer, an object falling toward a black hole would appear to slow down asymptotically as it approaches the event horizon, never seeming to actually cross it, though it would be progressively frozen and redshifted due to the extreme gravitational redshift. However, from the perspective of the falling object, it would cross the event horizon in a finite amount of time and continue toward the inevitable central singularity, where the known laws of physics completely break down. Black holes can be detected in several key ways. Many exist in binary systems with normal companion stars, gravitationally stripping material from the companion star, which forms a rotating accretion disk around the black hole. As this material spirals inward, friction heats it to temperatures of millions of degrees, emitting intense X-rays that we can detect with space telescopes. The first strong stellar black hole candidate, Cygnus X1, was discovered in this manner in 1964 when it was detected as a powerful X-ray source in the constellation Cygnus, the Swan. In 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, project successfully detected gravitational waves for the very first time, ripples in the fabric of space-time itself, produced by the merger of two black holes approximately 1.3 billion light-years away. This historic discovery, which was awarded the Nobel Prize in Physics in 2017, opened a completely new observational window onto the universe and dramatically confirmed one of the most extraordinary predictions of Einstein's theory. Since then, dozens of additional black hole mergers have been detected, revealing a population of these exotic objects far more abundant and diverse than previously anticipated. In 2019, the Event Horizon Telescope (EHT) project achieved another extraordinary feat, capturing the very first direct image of the event horizon of a supermassive black hole at the center of the galaxy M87, located approximately 55 million light-years away. The image showed a bright ring of emission surrounding a central dark shadow, exactly as predicted by simulations based on general relativity. This specific black hole has a mass of approximately 6.5 billion times the mass of the Sun, and an event horizon with a diameter of about 40 billion kilometers, which is larger than the entire orbit of Neptune. Nebulae also form an integral, beautiful part of the cosmic landscape of our galaxy. These vast clouds of interstellar gas and dust are the active locations where new stars are born and where dying stars return their enriched material to the interstellar medium. The Orion Nebula, M42. Situated approximately 1,344 light-years away, is probably the most famous and extensively studied emission nebula. Visible to the naked eye as a diffuse patch in the sword of the celestial hunter, this massive stellar nursery spans approximately 24 light-years in diameter and contains enough raw material to form thousands of stars like the Sun. Chapter 6. The Milky Way and the Galactic Heart. Within the Orion Nebula, astronomers have successfully identified numerous protoplanetary disks, or proplyds, which are structures of rotating gas and dust surrounding young stars where planets are actively forming right now. These direct observations of planetary systems in their birth stages allow us to better comprehend the mechanisms by which our own solar system arose approximately 4.6 billion years ago. The so-called Orion trapezium, a compact cluster of young, massive stars at the heart of the nebula, provides the majority of the powerful ultraviolet energy that ionizes the surrounding gas, causing the nebula to shine with its characteristic greenish and reddish glow. Another spectacular nebula is the Crab Nebula, the remnant of a supernova that exploded in the year 1054 and was meticulously recorded by Chinese and Arab astronomers of the era. This nebula is situated approximately 6,500 light-years away in the constellation Taurus, and it is expanding rapidly at a velocity of about 1,500 kilometers per second. At its very center resides a pulsar that spins 30 times per second, the collapsed, dense remnant of the star that exploded nearly a millennium ago. This pulsar, known as PSR B0531+21, continuously feeds the nebula with energy, accelerating charged particles to near light speeds and creating intricate structures of bright filaments that visibly change even on timescales of weeks. The Eagle Nebula, immortalized by the iconic Pillars of Creation image captured by the Hubble Space Telescope in 1995, is another active stellar nursery, located approximately 7,000 light-years away. The pillars themselves are monumental structures of cold gas and dust, each spanning several light-years in length, which are being gradually eroded by the intense ultraviolet radiation from nearby massive young stars. At the tips of these towering pillars, small, denser gas globules called EGGs, evaporating gaseous globules, contain embryonic stars that are currently in the process of formation, temporarily shielded from the destructive radiation by the surrounding columns of denser material. The Helix Nebula, situated at approximately 655 light-years away in the constellation Aquarius, represents the eventual fate that awaits our Sun in about 5 billion years. This planetary nebula, despite its misleading name, which has nothing to do with planets, is the ejected outer envelope of a Sun-like star that reached the end of its life. At the center of the nebula, an extremely hot white dwarf intensely shines, the exposed core of the dying star, with a surface temperature of approximately 120,000 Kelvin. The ultraviolet radiation from this hot white dwarf ionizes the expelled gas, causing it to glow in vibrant colors of blue, green, and red, creating one of the most beautiful and poetic vistas in the cosmos. These impressive nebulae, the titanic stars, and the exotic objects we have visited on our journey are not isolated entities floating randomly in the infinite vacuum. They are all integral working components of a much larger and grander structure, our home galaxy, the Milky Way. This vast stellar system is our cosmic island of light in the surrounding darkness, containing everything we can directly see with the naked eye in the night sky, with the exception of a few extremely faint neighboring satellite galaxies. The Milky Way is classified as a barred spiral galaxy, one of the most common galaxy shapes in the observable universe. It contains between 200 billion and 400 billion individual stars, although the exact number is extraordinarily difficult to determine due to the light absorption caused by interstellar dust and the inherent limitations of our observations from our vantage point within the galaxy itself. In addition to these countless stars, the Milky Way harbors enormous quantities of interstellar gas, primarily hydrogen and helium, as well as cosmic dust composed of heavy elements like carbon, silicon, and iron, forged in the nuclear furnaces of previous generations of stars. The total estimated mass of interstellar gas in the galaxy is approximately 10 billion to 15 billion solar masses. The main diameter of the Milky Way's stellar disk is approximately 100,000 to 180,000 light-years, depending on where one defines the diffuse outer boundary of the galaxy. The disk has a relatively small thickness compared to its diameter, only approximately 1,000 light-years in the thinnest regions, giving it an appearance similar to a flat record when viewed edge-on. However, the disk is not perfectly flat like a coin. It exhibits a notable warp in its outer regions, likely caused by powerful gravitational interactions with nearby satellite galaxies, such as the Magellanic Clouds that orbit our galaxy. Our solar system is situated in what is known as the Orion Arm, or Orion Spur, a minor structure located between two larger main spiral arms, the Sagittarius Arm toward the galactic interior and the Perseus Arm toward the exterior. We are located approximately 26,000 to 28,000 light-years from the galactic center, placed quite far from the nucleus but not in the extreme outer regions. Our Sun orbits the galactic center at a speed of approximately 220 kilometers per second, completing one full orbit every 225 million to 250 million years, a period of time famously known as a galactic year or cosmic year. This means that since the time the last dinosaurs walked the Earth, our solar system has completed barely one single orbit around the galactic center. From our perspective, deep inside the galactic disk, we perceive the Milky Way as a diffuse, luminous band stretching across the night sky from horizon to horizon. This visible band is simply our internal view of the galactic disk,
looking through the myriad of stars that compose it in all directions. The brightest regions of the band, which are visible toward the constellations of Sagittarius and Scorpius during the summer months in the northern hemisphere, correspond to our view looking directly toward the galactic center, where the density of stars is considerably higher. The dimmer regions in the opposite direction look out toward the less populated outer regions of the galaxy. At the very heart of the Milky Way, a remarkable region exists called the galactic bulge, a spheroidal thickening of the disk that extends approximately 3,000 light-years perpendicular to the galactic plane and has an elongated bar-like shape when viewed from above. This central region contains an extremely high concentration of stars, primarily ancient population 2 stars that formed in the earliest stages of the galaxy's history, more than 10 billion years ago. The stellar density in the bulge is so extraordinarily high that if we lived on a planet orbiting a star in this region, our night sky would be illuminated by thousands of stars brighter than Sirius, creating a celestial spectacle truly unimaginable for us in our relatively tranquil location in the galactic suburbs. But the most fascinating and mysterious element of the galactic center is not the stellar bulge itself, but what lurks at its absolute core, a supermassive black hole known as Sagittarius A, pronounced Sagittarius A star. This invisible gravitational behemoth has a mass of approximately 4.15 million times the mass of the Sun, an amount difficult to fully conceive, yet contained within an event horizon with a diameter of only about 24 million kilometers, which is smaller than the orbit of Mercury around the Sun. The existence of Sagittarius A star was originally inferred from the observed orbits of stars extremely close to the galactic center. By meticulously tracking the movement of these S-stars for decades using some of the world's most powerful telescopes, including the Very Large Telescope in Chile and the Keck telescopes in Hawaii, astronomers were able to calculate with extraordinary precision the mass of the invisible object around which these stars orbit. One star in particular, designated as S2 or S0-2, has an extremely elliptical orbit that brings it to within only 17 light-hours of the black hole at its closest approach, traveling at speeds that reach approximately 3% of the speed of light. This star completes one orbit every 16 years, providing direct, compelling evidence of the supermassive black hole's presence. In May of 2022, the Event Horizon Telescope, EHT, published the first direct image of Sagittarius A Stapper, showing the characteristic ring of bright emission surrounding the dark shadow of the black hole, similar to the previous image of the black hole in M87 Stapper, but technically much more challenging to obtain due to the rapid variability of the material frantically orbiting our galactic black hole. This historic image visually and directly confirmed what decades of indirect observations had suggested, that at the heart of our home galaxy resides one of the most extreme and mysterious objects in the known universe. Sagittarius A is surprisingly quiescent compared to the supermassive black holes in the nuclei of many other active galaxies. It consumes relatively little material and emits low levels of radiation, suggesting it is in a relatively inactive or dormant state in astronomical terms. However, it occasionally experiences bright flares when clouds of gas or stellar material approach too closely and are partially accreted. X-ray observations have successfully detected these sporadic flares, which can increase the black hole's brightness by factors of several hundred for periods of hours before fading away again. It is now widely believed that virtually all large, massive galaxies harbor supermassive black holes in their centers, with masses ranging from millions up to tens of billions of solar masses. The tight correlation found between the mass of the central black hole and the properties of the host galaxy, particularly the mass of the stellar bulge, suggests a deep and fundamental connection between the evolution of supermassive black holes and the formation of galaxies themselves. However, the precise details of this crucial connection are still not fully understood and remain the subject of intense, ongoing research. Surrounding the visible disk and the central bulge of the Milky Way is the galactic halo, an approximately spherical region that extends up to about 200,000 light-years or even farther from the galactic center, enveloping the entire visible structure of the galaxy. This immense halo contains globular clusters, compact spherical groupings of ancient stars that can contain anywhere from tens of thousands up to several million individual stars densely packed together. The Milky Way has approximately 150 to 200 known globular clusters orbiting within the halo, although more may exist hidden by galactic dust or simply too faint to detect with current instruments. The stars within globular clusters are extremely ancient, typically having ages of 10 billion to 13 billion years, formed in the very earliest stages of the universe's history, shortly after the Big Bang. These stars are almost exclusively population 2, extremely poor in heavy elements compared to younger stars like our Sun, reflecting the fact that they formed when the universe contained far less metallicity than it does today. But these ancient stellar clusters are not the only inhabitants of the vast galactic halo. The halo also contains another much more mysterious and invisible component: dark matter, an enigmatic form of matter that neither emits, absorbs, nor reflects electromagnetic light of any kind, but which is unequivocally revealed through its powerful gravitational effects on visible matter. In fact, it is estimated that approximately 85% of the total mass of the Milky Way is composed of this invisible dark matter, with normal matter, all the stars, gas, dust, and everything we can directly observe, representing only a small fraction of the total. The distribution of dark matter in the halo extends far beyond the visible disk of the galaxy, creating a massive gravitational well that holds the entire galactic structure together and prevents the stars in the outer regions from escaping into intergalactic space. The Milky Way does not exist in cosmic isolation, floating alone in the void. It gravitationally interacts with numerous smaller satellite galaxies that orbit around it like miniature moons, the most prominent and well-known being the Large Magellanic Cloud and the Small Magellanic Cloud, both visible to the naked eye from the southern hemisphere as bright, nebulous patches in the night sky. These dwarf irregular galaxies contain billions of stars and are being gradually torn apart and absorbed by the relentless gravity of the Milky Way, in a process of galactic cannibalism that will eventually incorporate them completely into our galaxy over the next several billions of years. Looking far into the distant cosmic future, the Milky Way is destined to experience a truly dramatic event, a spectacular collision and merger with the Andromeda Galaxy, our largest galactic neighbor. Andromeda is currently approaching us at a speed of approximately 110 kilometers per second, and astronomers predict that the two galaxies will begin to gravitationally interact significantly within approximately 4 billion years. The resulting merger, which will take several additional billions of years to fully complete, will create a new, giant elliptical galaxy that scientists have informally dubbed Milkomeda or Lactomeda, combining the names of both progenitor galaxies. Despite this sounding catastrophic, individual stellar collisions will be extremely rare during this galactic merger due to the immense distances separating individual stars. Our Sun, if it still exists at that distant time, it will be nearing the end of its main sequence life, will likely survive the encounter intact, although it could be flung into a completely different orbit within the merged galaxy, or even launched out into intergalactic space.
The night sky viewed from Earth, if our planet still exists by then, will be absolutely spectacular during the most active phases of the merger, with Andromeda dominating the firmament and dramatic star formation events creating brilliant regions of ionized gas visible to the naked eye even during the day. Chapter 7. Beyond Our Galaxy, the Limits of the Observable Universe. Abandoning the familiar confines of the Milky Way, our mental journey now extends toward truly cosmic scales, toward the immense structures that define the large-scale architecture of the universe. The solar system, along with all its planets, moons, and asteroids, together with our closest stellar neighbors that we explored in the initial stages of our voyage, are nothing more than grains of sand on an incomprehensibly vast cosmic beach. Our home galaxy, with its hundreds of billions of stars, is itself merely a component of a much larger structure known as the local group of galaxies. This gravitationally bound grouping of galaxies occupies a region of space with a diameter of approximately 10 million light-years and contains more than 50 identified galaxies, although the exact number remains uncertain because small, faint dwarf galaxies are constantly being discovered, having previously gone unnoticed. The three dominant galaxies of the local group are the Milky Way, the Andromeda Galaxy, also known as GNU M31, and the Triangulum Galaxy, M33. These three spiral galaxies contain the vast majority of the group's stellar mass, while the dozens of smaller galaxies are primarily dwarf elliptical and irregular galaxies that orbit around the three large spirals as modest satellites. The total mass of the local group is estimated to be approximately 1.5 to 3 trillion solar masses, although the majority of this mass exists in the form of invisible dark matter that envelops each galaxy in a massive, unseen halo. The Andromeda Galaxy, situated at approximately 2.5 million light-years from Earth, is the largest spiral galaxy in the local group and is slightly more massive than the Milky Way, with an estimated stellar mass of approximately 1 trillion solar masses. With a disk diameter of about 220,000 light-years, Andromeda is also significantly more spatially extensive than our galaxy. Like the Milky Way, Andromeda harbors a supermassive black hole at its center, though it is considerably more massive than Sagittarius A star, with a mass of approximately 100 to 200 million solar masses. Andromeda is visible to the naked eye from dark locations in the northern hemisphere as a small, faint, diffuse smudge in the constellation that bears its name. This tenuous spot of light that we can barely distinguish is actually the combined light of 1 trillion suns, which has traveled for 2.5 million years across the cold intergalactic void before finally reaching our eyes. When we look at Andromeda, we are seeing the galaxy as it was 2.5 million years ago, an epoch when our hominid ancestors were barely beginning to walk upright on the African savannas, manufacturing the very first stone tools. The Triangulum Galaxy, the third largest in the local group, lies at approximately 3 million light-years away and contains approximately 40 billion stars. Although it is significantly smaller than the Milky Way and Andromeda, is notable for its high star formation rate, featuring vast regions of ionized hydrogen, where new generations of stars are being born at a prodigious pace. The galaxy lacks a significant central bulge, suggesting it has never experienced a major galactic merger in its history, thereby maintaining its relatively pristine and immaculate spiral structure. The local group, despite its unassuming name, is not an isolated structure floating alone in the cosmic vacuum. Instead, it is simply a minor subcomponent of a much larger and grander structure known as the Virgo supercluster, also informally called the local supercluster. This colossal structure spans approximately 110 million light-years in diameter and contains at least 100 groups and clusters of galaxies, with a total estimated mass of approximately 100 trillion solar masses. The gravitational center of the Virgo supercluster is the Virgo cluster, a massive concentration of more than 1,300 galaxies, situated approximately 54 million light-years away in the direction of the constellation Virgo. This cluster is dominated by giant elliptical galaxies, including M87, the galaxy whose supermassive black hole was first successfully photographed by the Event Horizon Telescope in April of 2019, a historic image that captured the imagination of the entire world. Text M87 is one of the most massive galaxies known in the nearby universe, with an estimated mass of approximately 2 to 3 trillion solar masses and containing up to 13,000 globular clusters, nearly 100 times more than the Milky Way. The gravity of the Virgo cluster is so immense and dominant that it is currently pulling the entire local group toward it at a speed of approximately 220 kilometers per second. However, this inexorable fall toward Virgo is not the only large-scale motion our region of space is experiencing. Detailed and meticulous studies of the peculiar velocities of galaxies in our cosmic neighborhood have revealed the existence of even more distant, massive concentrations of matter that exert significant gravitational influences over vast regions of space spanning hundreds of millions of light-years. One of these mysterious structures is the Great Attractor, a massive gravitational anomaly located approximately 150 to 250 million light-years away in the direction of the constellations Hydra and Centaurus. This region of space exerts such a powerful gravitational pull that it is dragging thousands of galaxies, including the entire Virgo supercluster, toward it at speeds of several hundreds of kilometers per second. The exact nature of the Great Attractor has been difficult to determine because it lies behind the plane of the Milky Way, in a region known as the Zone of Avoidance, where the dust and stars of our own galaxy obscure our view of the deep space beyond. Observations at wavelengths that can successfully penetrate galactic dust, such as infrared and X-rays, have revealed that the Great Attractor is actually part of an even larger, more massive structure, the Laniakea supercluster. This name, which means immeasurable heaven in Hawaiian, was proposed in 2014 by a team of astronomers who mapped the movements of more than 8,000 galaxies to delineate the boundaries of this colossal superstructure. Laniakea spans approximately 520 million light-years in diameter and contains the mass of approximately 100 million billion suns, or roughly 100 quadrillion solar masses. This superstructure includes the Virgo supercluster, the Great Attractor, the Hydra-Centaurus supercluster, and several other minor superclusters, all bound together in a vast filament of galaxies that are gravitationally flowing toward a common center. We are, in a very real sense, residents of Laniakea, traveling along with hundreds of thousands of galaxies in a cosmic dance orchestrated by gravity across timescales of billions of years. But even Laniakea, with all its nearly incomprehensible immensity, is only one component of the universe's large-scale structure, a complex, intricate pattern of galactic filaments, monumental walls, and gigantic voids that extends to the very limits of the observable universe. This structure is sometimes referred to as the cosmic web, a term that beautifully captures its spiderweb-like appearance when visualized in computer simulations or three-dimensional maps of galaxy distribution. Galactic filaments are vast, linear structures of galaxies that stretch over hundreds of millions of light-years, connecting massive galaxy clusters like bright threads in the darkness of space. These structures formed in the first few billion years after the Big Bang,
when dark matter began to collapse gravitationally into dense filaments, dragging along ordinary gas that eventually condensed into the galaxies we see today. Filaments are the densest regions of the universe outside the galaxy clusters themselves, and they contain the majority of the cosmos's normal baryonic matter. Between these filaments are the cosmic voids, vast regions of space that contain very few galaxies. These voids can have diameters of 100 to 400 million light-years, volumes so immense that they defy human comprehension. The largest known void, the Boötes void, or the Great Void, is approximately 330 million light-years in diameter and contains only a few dozen galaxies, whereas a comparable volume in a region of average density would contain thousands of galaxies. These voids are not entirely empty, containing tenuous filaments of dark matter and scattered dwarf galaxies, but they are extraordinarily underpopulated compared to the surrounding universe. Some of the largest single structures in the universe are the galactic walls, or Great Walls, massive concentrations of galaxies that form sheet-like or wall-like structures separating adjacent voids. The Sloan Great Wall, discovered in 2003, spans more than 1.37 billion light-years, making it one of the largest structures ever observed. However, even this pales in comparison to the Hercules Corona Borealis Great Wall, discovered in 2013, which stretches for approximately 10 billion light-years, roughly 10% of the diameter of the observable universe. The mere existence of a structure as gigantic as the Hercules Corona Borealis Great Wall raises profound questions about our understanding of cosmology. According to the cosmological principle, a fundamental assumption in modern cosmology, the universe should be approximately homogeneous and isotropic on sufficiently large scales, meaning there should be no preferred direction or special location. However, simulations based on our current models of universe evolution suggest that structures as large as the Hercules Corona Borealis Great Wall simply should not have had time to form in the 13.8 billion years since the Big Bang. This enigma serves as a powerful reminder that, despite all our scientific advances, there are still fundamental aspects of the universe that we do not fully comprehend. Our cosmological models are extraordinarily successful at explaining the vast majority of observations, from the cosmic microwave background radiation to the accelerated expansion of the universe, but we occasionally encounter anomalies that challenge our theoretical expectations. According to widely accepted modern cosmological concepts, space itself is constantly expanding, carrying with it the galaxies embedded in its fabric. This expansion is not an explosion of matter moving through pre-existing space, as is often misunderstood, but rather an expansion of space itself. Distant galaxies are not moving away from us by traveling through space, but rather the space between us and them is growing, increasing the distance. Crucially, the speed of this expansion depends on the distance between the objects. The farther away an object is from the observer, the faster the distance between them increases due to the expansion of the intervening space. This relationship, discovered by Edwin Hubble in 1929, is known as Hubble's law. Furthermore, this recession velocity is not limited by the speed of light because it is not motion through space, but an expansion of space itself. This means that at a certain sufficiently large distance, objects recede from us faster than the speed of light, and therefore become mutually unobservable. Their light signals can never reach us. Observations of the cosmic microwave background, radiation, the residual glow of the Big Bang that fills all space, coupled with measurements of the universe's current expansion rate, indicate that the region of the universe accessible to observation from Earth is a sphere of approximately 93 billion light-years in diameter. This may sound paradoxical given that the universe is only 13.8 billion years old, but it is explained by the fact that space itself has expanded throughout that time, stretching the light that finally reaches us. According to the theory of general relativity, we can only see and causally interact with those objects that are within this sphere, our cosmological horizon.
This region of space is called the metagalaxy, or the observable universe, and it represents everything we can possibly know about the cosmos through astronomical observations. The metagalaxy contains approximately 2 trillion galaxies, each containing hundreds of billions of stars, a number so vast that it exceeds the number of grains of sand on all the beaches of Earth. But here, a profound and philosophical question arises that has intrigued cosmologists and philosophers alike. Is the metagalaxy the entire universe, or is it simply a small part of a much vaster cosmos that stretches beyond our observable horizon? This question, by its very nature, touches the limits of empirical science, because everything beyond the cosmological horizon is, in principle, unobservable from our location in space and time. Hypothetically, vast and unknown structures could exist beyond the visible region of outer space. These potential entities are termed extra-metagalactic objects, and unfortunately, by definition, it is currently impossible to study them using conventional scientific methods based on direct observation. However, some scientists have proposed indirect methods to infer their existence. For instance, some astronomical objects at the very edge of the visible universe do not move exactly as they should according to available data and standard cosmological models. These rare instances of anomalous motion could serve as subtle evidence for the possible presence of some massive structures outside the metagalaxy. Their gravitational pull, though attenuated by the immense distance, could permeate the surrounding space, subtly influencing objects within our observable horizon. This hypothesis, while speculative, is in principle testable through increasingly precise measurements of galactic movements. There are numerous hypotheses regarding the structure of the universe beyond the metagalaxy, but most of them are of a rather metaphysical nature, bordering the limits between science and philosophy. For example, there is a viewpoint according to which outside the boundaries of the observable universe, there is simply no time or space in our usual everyday comprehension. The known physical laws, validated by countless experiments and observations, might not hold true, and fundamental concepts like matter, substance, energy, and even causality might become nonsensical, lacking any meaning in a realm so radically different from our own. A logical development of this provocative hypothesis is the idea that the metagalaxy is only an infinitesimal part of an even more complex cosmic superstructure of truly unimaginable scale, whose complete structure and total dimensions we are, in principle, unable to conceive with our minds evolved to understand the world on human scales. It is possible that this hypothetical superstructure could be located in a multidimensional space with more dimensions than the 3 spatial and 1 temporal that we experience, or rely on completely unknown physical principles, radically different from everything we have encountered in our scientific investigations to date. The metagalaxy could therefore be only a minor detail, a small bubble, or a partial and limited reflection of this incredible, unimaginable superstructure. Some theoretical physicists have speculated that our observable universe might be analogous to a single drop of water in an infinite ocean, completely incapable of perceiving the vastness of the ocean surrounding it. Some interpretations of the anthropic principle, which suggests that the physical laws of our universe appear to be finely tuned to permit the existence of conscious life, propose the existence of other universes, or worlds, outside the visible universe, each with different values of fundamental constants, such as the speed of light, c. Planck's constant, the electron charge, or the gravitational constant. In some of these hypothetical universes,
stars might not form. In others, atoms might be unstable. In still others, the universe might collapse back onto itself seconds after birth. This hypothesis is closely related to the idea of the multiverse, a concept that can be represented as a kind of cosmic foam formed by countless separate bubbles, partitioned by thin yet absolutely insurmountable barriers. Each bubble would be a completely separate universe with its own unique set of physical laws, perhaps radically different from those to which we are accustomed. In some of these universes, the fundamental forces might have different intensities. In others, completely new forces might exist that have no analog in our cosmos. In still others, the dimensions of space might be different, with two-dimensional or 10-dimensional universes being equally possible in principle. The most radical and philosophically challenging hypotheses entirely deny our world an objective, independent reality. According to these controversial assumptions, the entire universe is merely a sophisticated simulation, like an incredibly advanced level of computer virtual reality running on a computational substrate that is fundamentally beyond our capacity to detect. As a general rule, such ideas presuppose the existence, outside our habitual reality, of some kind of superior being, a transcendent intelligence, or a technological supercivilization whose level of development and capabilities are vastly higher than ours, so superior to us as we are to single-celled bacteria. The objects, entities, and capabilities of such beings or civilizations are likely mysterious and incomprehensible to our current level of understanding, as incomprehensible as quantum physics would be to an observer from the 14th century. Their motivations for creating a simulation of our universe, if we truly live in one, might be completely inscrutable to us. However, it is highly likely, and perhaps even necessarily true, that it is impossible to definitively prove or refute such hypotheses using the scientific method, because any evidence we might find could merely be part of the simulation itself. Space exploration, in all its forms, from sending robotic probes to the most sophisticated telescopic observations, is a complex, challenging, dangerous, and profoundly exciting ongoing process. Given the near infinite diversity of space objects, cosmic phenomena, and unanswered questions, this process of discovery could last almost indefinitely, potentially extending as long as human civilization exists, or any successor civilization that arises from us. Every day, every week, every year, humanity learns something new and astonishing about the universe we inhabit. Every discovery, from potentially habitable exoplanets to gravitational waves generated by merging black holes, from the first galaxies formed at the cosmic dawn to the mysterious dark energy that is accelerating the expansion of the universe, expands the horizons of our knowledge and raises new questions we hadn't even imagined. This means, in a deep and exciting sense, that our interstellar journey, our voyage of cosmic discovery, is barely beginning. We have taken the first tentative steps, sent the first probes beyond our solar system, captured the first images of black holes, and detected the first gravitational waves. But the universe is vast beyond all comprehension, and every answer we find generates a dozen new questions. Future generations will build more powerful telescopes, send out more ambitious missions, and develop more comprehensive theories. Perhaps one day, in a future we cannot predict, humanity, or its technological descendants, will develop the capability to actually travel among the stars, not just in imagination, but physically, converting this mental journey we have undertaken today into a tangible reality. Until then, we continue to gaze upwards with awe and curiosity toward that night sky filled with stars that has fascinated humanity ever since our remotest ancestors first lifted their eyes to the firmament. And in every point of light we see, we now know there is not just a star, but potentially whole worlds, cosmic stories of stellar birth and death, and mysteries waiting to be unveiled. The cosmos calls us, and the exploration continues.